Hello class, today's lesson is all about the combination or the network circuit. In the past, we have talked about a series circuit and parallel circuit independently, but today we're going to combine them. So we call them combination or a network circuit. So before we get into the analysis of the network circuit, let's take a look at the device that measures current and voltage. So we use an ammeter. An ammeter is used to measure the current in any branch or part of a circuit. And the reason we have to place an ammeter in series with the resistance is that you have the same current running through a loop. So I'll just draw a simple circuit here in series. I'll put three resistors. So let's say that I want to measure the ammeter in R1. So you have the potential difference or the voltage coming here from the positive terminal of the battery running this way. When the current runs through the R1, it also goes through R2 and R3, then finally returns back to the power source or the battery. So if I were to measure the current that is running through this R1, I have to put the ammeter either this way or this way. In a series circuit, recall that the current is the same as the total current of the system. So it actually does not matter where I put the ammeter as long as it is in series with the device that I am measuring. And so we always have to put the ammeter in series with the resistance. So ammeter has a symbol of the letter A inside a circle. And this is always in series with the resistance that you're measuring. The voltmeter The voltmeter is a device that measures the voltage of a resistance of a resistor. So a voltmeter is a symbol with a V inside a circle. So if I were to measure again the voltage in R1, I have to remember that if this is a series circuit, the current will be the same in that resistance as the total current of the system. But in a parallel circuit, what they have is the voltage. So the reason we need to attach the voltmeter in parallel with the resistor like this is that we need to measure how much voltage is entering R1 and how much voltage is coming out of R1. So this is called the V drop and this is called the V rise. Remember that, let's say you have 9 volts coming out of this battery. What goes into the first resistor here, we call the V drop, is going to be the pressure or the potential difference that kicks the electrons or the current to operate this resistor here, which means the voltage is going to decrease as it leaves this resistor. Recall that the resistor resists the flow of current, so it will make the potential difference lower as it comes out of this resistor here. So it needs to be in parallel with the resistance that you're measuring so that you can measure the voltage drop, what goes in, and the voltage rise, what comes out of that resistance that we are trying to measure. So a voltmeter is connected in parallel with the resistance that you're measuring the voltage of. So when we talk about combination or network series, there are some strategies that we can follow so that we can analyze them in steps. When you look at resistors that are connected in parallel, we can combine them and find the single equivalent resistance that can replace those different resistors connected in series or parallel. So we can do that when we find the clusters in series and clusters in parallel. Combine them first until we simplify them enough that we can reduce the circuit to a single resistance, and that would be the total circuit resistance of the combination circuit. From then, we can calculate the total current of the entire circuit, and in order for us to analyze the individual current of each single resistor in this combination circuit, we need to be able to apply Kirchhoff's rules in terms of the loop and junction rules. So as a problem-solving strategy, it will be helpful to remember the following to figure out which resistors are in parallel and which ones are in series. Remember that those resistors in parallel have separate current path, so they will have the same potential difference across them. So these are the ones in parallel. Parallel would have the same voltage across the individual resistor. Resistors in series, they only have one current conducting path, so they will have the same current as the total current that is running through the entire circuit. So knowing Kirchhoff's rules will be very helpful in analyzing our network or combination circuit. So let's jump right into an example of a combination circuit. So here we have a resistor, 30 ohm resistor connected in parallel with a 20 ohm resistor. The parallel connection is placed in series with an 80 ohm resistor. So they're both in series with this 8 ohm resistor. So I'm going to start with a battery. Remember that there are many ways to draw a circuit. So just taking a look, these two resistors are in parallel with each other, but in series with the 80 ohm resistor. So I'm going to start with this one here because they're in series with that 8 ohm resistor. So here is the 8 ohm resistor, and I'm going to make my two resistors here in series with that. So here's one possible diagram that I have drawn here. So we have 60 volts of potential. This is 8 ohm resistor, and this is our 30 ohms, and this is our 20 ohm. As you can see, there's a junction right here, so these two are in parallel, but together they are in series with that 8 ohm resistor. So in our circuit analysis, we could first figure out the equivalent resistance of these two. So the equivalent resistance is 1 over R equivalent resistance is 1 over 30 plus 1 over 20. And that would give us an equivalent resistance of, remember you can use your buttons with x to the power of -1 or 1 over x. So 30 second function x -1 plus 20, second function x to the negative 1 equals, and then second function x to the negative 1 one more time, and the equivalent resistance is 12 ohms. That 12 ohm is now in series with the 8 ohms. So our total resistance is 8 plus 12, which is 20 ohm of total resistance. So we have found the total resistance. We have a total voltage here. Our EMF is 60 volts. We can figure out the individual volts or the individual current. But first, because I have simplified this diagram, once I've combined these two, what my simplified diagram now looks like is actually this. So this, we still have the 8 ohms, but now this equivalent resistance here is in series with the 8 ohms. So because these two are in series, they will have the same current as the total current that we have. So I can calculate the total current and it will be the same as the current here, which is, I'm going to call this one R1 and this one R2 and this one R3. So this will be IT is equal to I1 equals I2 plus I3, because those two are in series or in parallel, although they're in series with the 8 ohm. So what I'm going to do is I'm going to calculate the total current first. So total volts divided by the total resistance. So this is 60 divided by 20. This is going to give us 3 amps of total current. So now we know that I1, the one that's 8 ohm, is going to have 3 amps of current. We still don't know the current in each of these 30 and the 20 ohms because they will not be the same. But what they will have is the same voltage because they are in parallel circuit. So what I'm going to now find is the V1, since I know the I and the R. So V equals I, R, and this is going to give me the current in one. The first resistor is 3 amps times 8 ohm, and this is going to give us 24 volts. Now remember that the total volts is 60 volts. So you have 60, take away 24, and that will be the remaining voltage. So if V1 is 24 volts, then V2, which is going to be equal to V3, will be 60 minus 24, which is 36 volts each. And if you combine the two, you will get the 60 volts. Okay, so we have analyzed the total resistance. So when you're doing a circuit analysis, you have to look at the total resistance, done. We have to look at the total current, done right here, and the total voltage, which is given. Then we have to look at the individual current. We have found I1. Now we got to find I2 equals V2 over R2, and this is 60 divided by 30, and I is 2 amps, so I2 is 2 amps, and I3 is V3 over R3. This is, our V2, my mistake here, my V2 is actually, V2 is 36 volts, not 60. So 36 divided by 30 is 1.2 amps of current running in the second resistor. And our V3 is 36 volts divided by 20, which is 1.8 amps. So if we find the total amperage of the circuit, you have 3 amps, which is the total current running through the system, and 1.2 plus 1.8 is also going to be equal to 3 amps. And this is why they are 3 amps together, because the 30 ohms and the 20 ohms are in parallel with each other, but together their current is also 3 amps, which is the same as the 3 amps running through the 8 ohm resistor. So we have finished our circuit analysis for this one. We got the individual currents and the individual voltages. And that is how you do a circuit analysis of a network or a combination circuit.